October 7th, 2025. NASA's Perseverance rover transmits an image that shouldn't exist, a faint object suspended in the Martian sky. Small, pale, and wrong. It isn't a star. It isn't a comet. It's 3E Atlas. The third confirmed interstellar visitor humanity has ever seen. But for the first time, it's been photographed not from Earth, but from another world. The data is clear. The rover's Mastcam Z camera detected an intense negative polarization, light behaving backward, scattering in reverse. The object's reflected spectrum doesn't match dust, ice, or gas. Instead, it aligns eerily with minerals once mapped on Mars itself. Even more unsettling, 3I Atlas hasn't changed speed, spin, or course despite active outgassing. That's not just unusual, it's unprecedented. What the Perseverance rover captured might not be a comet at all. It might be something older, heavier, and engineered with purpose, and in just over 3 weeks it will vanish behind the sun, a perfect window to disappear. This is where the story of 3I Atlas turns, and it begins with light, behaving in a way the universe was never supposed to allow. When astronomers analysed the Perseverance image, the first anomaly wasn't shape or brightness, it was polarization. Light from 3I Atlas wasn't just reflected, it was inverted. Polarization describes how light waves oscillate as they travel. Ordinary comets, filled with dusty ice and volatile gases, polarize sunlight in predictable ways. Typically positive polarization at small phase angles, meaning light scatters outward from the sun's reflection. But what the Mastcam Z camera detected was extreme negative polarization. Light waves aligned against the expected direction, bending toward the source instead of away. On paper, that shouldn't happen. Dr. Nandini Gupta from NASA's Jet Propulsion Laboratory called the data a violation of the scattering models we use for all known cometary surfaces. The reflection was so intense that the polarization ratio dropped to -6.8%, almost identical to metallic alloys under direct sunlight, not carbon or ice. To verify, the team cross-checked with the AMAVEN's ultraviolet spectrometer in Mars orbit. The readings matched. Whatever 3I Atlas was, its surface wasn't behaving like ice. It was behaving like something polished, structured, or fused at extremely high temperature. That's when suspicion turned to the chemical composition. If the light wasn't behaving naturally, maybe the surface wasn't natural either. When a comet's coma scatters sunlight, the angle-dependent polarization helps scientists estimate particle size. Most icy grains are submicron. But 3I Atlas reflected light as if its surface were composed of large uniform plates, like scales or panels. Even the polarization phase curve was smooth, with no chaotic dips. It was, as one researcher described, the signature of order, the problem. There is no known natural process that creates that kind of uniformity on a fast-moving interstellar body. At the European Southern Observatory, a parallel analysis was performed using data from the VLT's FORS2 polarimeter. Their measurements confirmed the anomaly and added something stranger. As 3I Atlas approached its current position, the degree of negative polarization increased sharply, as though the surface were actively adjusting to sunlight. For comets, polarization usually weakens with distance from the sun. Here it was intensifying. Dr. Elena Markovic, who led the analysis, said quietly during a press briefing, "It's as if the object knows where the sun is." By early October, 3 independent observatories, Mars, Earth, and orbit, had confirmed the same optical behavior. Light bending in reverse, a growing polarization field, a stable reflection that refused to fluctuate with rotation. Every explanation on the table led to contradiction. If it's metallic, it shouldn't outgas. If it's icy, it shouldn't polarize negatively. If it's rocky, it shouldn't glow this way under UV exposure. And yet 3I Atlas displayed all 3 traits: metal, gas, rock, coexisting in one coherent system. Avi Loeb, the Harvard astrophysicist who's been at the center of the interstellar object debate since Oumuamua, wrote in his October 3rd memo, "If polarization tells us anything, it's surface structure, and 3I Atlas appears structured, deliberately or otherwise. The question is whether nature built it that way, or something else did. As the data spread across research networks, skeptics pointed out that negative polarization could result from layered transparent coatings, like fused silica or glassy carbon. But even those require controlled heat and uniformity far beyond random formation. Whatever process shaped this object, it wasn't simple crystallization in deep space. By the end of the week, the discussion had shifted from what caused it to where it came from. Some argued that such a surface could only form within a planetary crust, not in interstellar space. And if that's true, then 3I Atlas isn't a comet at all. It's debris, something that once belonged to a planet. But before that hypothesis could take hold, another discovery complicated everything further. The chemical spectrum behind that strange light didn't just hint at a rocky composition, it matched something disturbingly familiar, the surface of Mars. And that's where the investigation takes its next turn, into a connection no one expected. When Perseverance's Mascamzede image was first processed, NASA's Jet Propulsion Laboratory uploaded the reflectance data to a comparative database, its standard procedure. The algorithm checks for known mineral signatures by matching absorption bands across visible and infrared wavelengths. The software cross-references thousands of geological samples from missions past, Gale Crater, Jezero Delta, even the dust analysed by Curiosity's ChemCam. Within minutes, an alert appeared on the screen. Spectral match, iron oxide 3, hematite, 87% confidence. Hematite, the iron oxide responsible for Mars' red hue. At first, the team dismissed it as coincidence. Iron oxides are common throughout the cosmos, but then the pattern deepened. A secondary peak emerged at 1.9 micrometers, a hydration band typical of clay-bearing rock. Another subtler signature aligned with olivine silicate, a mineral abundant near Jezero Crater, the very site where Perseverance currently operates. By the end of the analysis, the software produced an improbable overlap. 3 key mineral signatures, hematite, hydrated silica and olivine, all consistent with Martian crust composition. And the odds of that combination occurring naturally on an interstellar object were vanishingly small. Planetary scientist Dr. Helena Ruiz put it bluntly in a closed NASA meeting later leaked to Science Daily. This thing doesn't look like a visitor, it looks like a refugee. If true, it would mean 3I Atlas wasn't born in another star system, but blasted out of a planetary surface, perhaps during a cataclysmic event billions of years ago. That's not unheard of. Martian meteorites, like the famous ALH 84001 found in Antarctica, have long proven that debris can travel from Mars to Earth, but never the other way around, and never across interstellar space. Here's where the data becomes haunting. When scientists compared isotopic ratios in the object's coma, specifically the oxygen triplet lines, they found a slight enrichment pattern identical to Martian atmospheric oxygen. That pattern is unique to Mars due to photochemical reactions in its thin CO2 atmosphere. 3I Atlas was venting the same isotopic ratio as if it carried trapped Martian air frozen within its body. Dr. Avi Loeb summarized the paradox in a single sentence. If these readings are real, 3I Atlas didn't just pass Mars, it remembers it. The Martian connection, however, raises impossible logistics. Even under the most extreme volcanic or impact scenarios, no known event on Mars could launch debris fast enough to escape not only Martian gravity, but also the Sun's. To achieve an interstellar trajectory, the ejection speed would need to exceed 60 kilometers per second, several times greater than the fastest ejector ever observed, unless the object didn't leave Mars by accident. Some astrophysicists suggested a secondary mechanism, propulsion through energetic decay or sustained outgassing acting like thrust. But that only works if the object has an internal energy source, which at the time was unproven. Still, it was enough to open the door to something larger, an object that wasn't just debris, but engineered debris, perhaps something once functional. In the following days, as data poured in from the Mars Reconnaissance Orbiter and from Earth-based telescopes like Subaru and Lowell, scientists noticed another connection: colour phase consistency. The reddish tint of 3I Atlas matched Martian regolith under the same solar angles, but with an added greenish fluorescence. That green emission didn't exist on Mars, at least not on the surface. This implied a hybrid material, Martian minerals fused with something foreign, possibly during re-entry, impact or fabrication. In Loeb's private notes, later published through the Galileo Project archives, He speculated the composition could represent a technological artifact using local Martian resources, a kind of off-world manufacturing. If confirmed, this would mean 3I Atlas is not only interstellar but interplanetary in origin. Of course, mainstream astronomers pushed back immediately. Dr. Simon Grigg of EA's Rosetta program argued that silicate and oxide overlaps are common in many rocky bodies. Spectral coincidence, he said, does not equal lineage. But even he admitted the isotopic ratios were deeply unusual. The debate fractured the community into two camps: those who believed the Martian resemblance was an analytical illusion, and those who saw it as a breadcrumb from the past, a clue linking Mars to a much older cosmic event. Meanwhile, Perseverance's next batch of images showed something no one had predicted. 3I Atlas's brightness curve remained constant for days. No flickering, no rotation dips, no Comet expansion. An interstellar body, venting gas in sunlight, should wobble and spin chaotically. This one didn't. It behaved as if balanced, deliberately stabilized, even as faint outgassing continued from one side. It was the next anomaly in a growing list, a comet that refused to act like one, a body with a Martian chemical memory, and now, a rotation problem that would break another fundamental rule of celestial mechanics. Because the next discovery showed that 3I Atlas was not only holding its path, it was holding it perfectly. When a comet outgasses, it breathes. As sunlight warms its surface, volatile ices sublimate into jets of vapor that burst outward. These microthrusts should cause tumbling, torque, and irregular rotation. No natural object of its size, estimated between 5 and 6 kilometers across, could maintain a stable attitude for weeks under such asymmetric forces. And yet, 3I Atlas does. From the moment Perseverance's Mastcam Z first captured its faint flare in the Martian dawn sky, observers noticed something strange. The coma expanded, but the nucleus did not brighten or dim as it rotated. Light curve data from both the Mars Rover and Earth-based telescopes remained flat, an almost perfectly horizontal line. It was the light curve of a spinning body locked in equilibrium. At the Harvard-Smithsonian Center for Astrophysics, Dr. William Rhodes ran a computational simulation based on the observed mass loss rate. The result: for 3I Atlas to remain this stable, the jets would need to fire with equal force across every hemisphere, timed to the object's rotation. That level of balance doesn't exist in nature. It has to be coordinated or coincidental to a degree that defies probability. Even its trajectory shows unnatural steadiness. Most interstellar comets enter hyperbolic orbits that bend slightly as outgassing shifts their center of mass. But when the ESA's Gaia Observatory recalculated 3I Atlas's path on October 3rd, the object's deviation from its initial vector was less than 0.001 degrees. That's stability on the level of engineered satellites. The outgassing is happening, Rhodes said in a press briefing. You can see the spectroscopic CO2 lines, but the motion doesn't respond. It's as if thrust is being compensated. The implication unsettled even the most conservative researchers. If the gas jets aren't altering its trajectory, what's countering them? Internal gyroscopic stabilization? Magnetic coupling with solar radiation? Or something unknown, a mechanism acting beneath the surface? When infrared data from the Mars Reconnaissance Orbiter came in, the mystery deepened. Thermal mapping revealed 4 distinct hot zones on the surface of 3I Atlas, each exactly symmetrical, evenly spaced along its equatorial ridge. At first glance, they looked like venting regions, but their heat signatures didn't fluctuate like cometary jets. They pulsed, periodically, every 11 minutes and 24 seconds. No natural process has ever produced rhythmic thermal pulses of that precision. To test for instrument error, the team compared readings across 3 orbit passes. The pulse interval remained identical to within half a second. For Loeb, that was the tipping point. He wrote, "A periodic pulse synchronized across multiple emission sites implies coordination. Nature favors chaos. Coordination means intent. Or at least designed skeptics, however, weren't ready to call it technological." Dr. Adrian Mears from ESA argued that 3I Atlas might contain stratified CO2 layers, releasing gas under cyclical stress fractures, creating a quasi-periodic outburst pattern. But to maintain timing that precise across multiple locations, the object would need to be rotating exactly once per cycle, except it wasn't. The object's rotation period, measured by Doppler shifts, was 16 hours and 52 minutes. The thermal pulses were every 11 minutes, unrelated, independent, and mathematically clean. That left physicists with an unsettling model, a non-rotating emission rhythm on a freely spinning body. Something inside was dictating its own clock. By early October, NASA's trajectory team tried to explain the stability with sheer mass. If 3I Atlas were unusually dense, its inertia could dampen jet effects. Using orbital data and outgassing estimates, they derived a preliminary mass of roughly 33 billion tons, making it one of the densest interstellar objects ever recorded. But density raised its own paradox. How can something so massive maintain active venting without gravitational collapse or disintegration? The mass didn't explain stability, it made it impossible. On October 5th, new radar scans from Earth's Deep Space Network resolved a shape model. 3I Atlas isn't spherical. It's elongated, like a fractured spindle roughly 6 kilometers long and 1.8 wide. Its rotation axis points within 1 degree of its solar trajectory, meaning it's travelling nose first, presenting minimal surface area to solar radiation. That alignment minimizes drag, maximizes stability, and keeps the same side facing the sun for long periods. It's the most efficient orientation possible for flight. Dr. Mears called it aerodynamic coincidence. Loeb called it navigation. And here's the strangest part. Despite the venting, despite the energy fluctuations, despite the growing coma, no debris trail has formed behind it. The object's ejected material disperses, then vanishes, ionized or absorbed into an unseen field. No dust, no tail, no decay pattern. By any metric, 3I Atlas should be spinning apart by now. Instead, it's gliding, steady, unwavering, deliberate. For some, that's the most disturbing fact of all, because when chaos behaves like order, the universe stops looking random. And yet the next set of findings would push the limits even further, because if the object's motion was impossible, its weight, its true, measured mass, was something no natural comet could ever support. The mystery of its balance was only the beginning. The real problem was its gravity. The first mass estimates for 3I Atlas came from simple orbital mechanics. By tracking how sunlight pressure and gravitational pull interacted over time, NASA's trajectory team expected to find a standard cometary mass, somewhere between 10 to the power of 9 and 10 to the power of 10 kilograms. But when they ran the calculations using data from both Earth and Mars, the result wasn't just off. It was off by 4 orders of magnitude. According to orbital perturbation analysis, the object's inertia, its resistance to deflection by solar radiation and gas venting, required a mass of roughly 3.3 times 10 to the 10th tons. 33 billion tons. For context, that's more than the combined weight of every skyscraper in New York City, drifting through space, perfectly balanced. To cross-check, ESA's Gaia and NASA's JPL independently modelled the solar radiation pressure on the object. If it were a normal comet, sunlight should have slowed it ever so slightly as photons transferred momentum to its surface. But after weeks of observation, 3I Atlas showed no measurable deceleration. It was behaving as if light pressure simply didn't apply. That led to a second calculation, one that assumed the object was reflecting sunlight rather than absorbing it. Even under that assumption, its reflectivity would need to exceed 0.95, comparable to polished aluminum, to maintain stability at its current velocity. No known comet or asteroid has ever displayed such high albedo while also outgassing CO2. Dr. Valentina Orlova of the Russian Academy of Sciences was the first to propose a radical explanation. If its density is so extreme, perhaps it isn't porous ice at all. Perhaps it's compacted matter, crystalline carbon, metallic silicate, or something we haven't classified yet. But when Loeb's team tried to model that density, another problem surfaced. For an object 6 kilometers long to reach that mass, its mean density would need to exceed 8 grams per cubic centimeter, denser than iron. A comet made of rock that heavy shouldn't be venting gas. It shouldn't even be intact. The outgassing pressure would have cracked it open. Unless, of course, the gas isn't coming from inside the rock, it's being released through it. That idea gained traction when spectroscopy from Mars Reconnaissance Orbiter picked up a subtle emission line. Carbon dioxide, yes, but also trace ammonia and something rarer, argon-40. Argon-40 is produced by the radioactive decay of potassium-40 in planetary crusts. That means 3I Atlas isn't just massive, it's geologically mature. It has internal isotopes that have been decaying for billions of years. No interstellar ice fragment could contain such a profile, only a planetary body could. And so the question sharpened. What kind of planetary body could survive interstellar travel intact? What could weigh this much, vent in rhythm, and remain stable under solar radiation? In early October, Loeb compared the mass ratio of 3I Atlas to the expected range of known objects. Oumuamua, the first interstellar visitor, had a mass-to-area ratio of about 0.1 grams per square centimetre. Comet Borisov was denser, around 1.0, 3I Atlas, somewhere between 30 and 50 grams per square centimetre. It wasn't just heavier, it was categorically different. A small team at Caltech began referring to it as a superbody, an object large enough to maintain self-gravity yet too small to be a planet. In one internal email, later leaked to Skywire, a researcher wrote, "If this mass holds, we may be looking at a fragment of a core, a planetary remnant stripped of crust and atmosphere wandering between stars." But that explanation collided with another mystery: temperature. Infrared data indicated surface temperatures far higher than expected, up to 410 Kelvin, or roughly 137 degrees Celsius. For a body at that distance from the Sun, the temperature should be under 250 Kelvin. Something inside was generating heat, preventing cooling, and maintaining the same rate day after day. When Perseverance's instruments recalibrated for atmospheric refraction, the readings didn't change. The heat wasn't an illusion, it was real. So what could create both mass and heat without collapsing the object? One possibility emerged, and it was as strange as the numbers themselves. If 3I Atlas contains compacted heavy elements, uranium, thorium, or even metallic hydrogen residues, then slow radioactive decay could explain both its density and warmth. But for that to happen, the object would need to have formed in the core of a planet far larger than Mars, maybe something Earth-sized or bigger, meaning it's a survivor, a piece of a destroyed world. Not everyone accepted that conclusion. ESA's Dr. Mears cautioned that the thermal readings could result from residual gas compression, jets forcing heat through subsurface fissures, but even he admitted that such energy would fade over time. 3I Atlas has been stable for months. The truth is, no one knows how an object this heavy can remain intact without some kind of internal architecture, natural or artificial. And that brings us to the next mystery, its glow. Because as the object's mass numbers were finalised, telescopes began detecting something else, an oscillating green emission that flickered like a heartbeat in the dark. It wasn't reflection, and it wasn't gas. It was light, and it was coming from within. That discovery would redefine everything scientists thought they knew about this object, because a comet may shine, but this one pulsed. The first to notice were the astronomers at Lowell Observatory in Arizona. On the night of October 6, 2025, they recorded a faint but repeating colour variation from 3E Atlas. Subtle at first, then unmistakable. Every 40 minutes, the object's hue shifted from dull grey to an iridescent green, then faded back again. It wasn't a reflection artifact. The pulse continued even when the sun's angle dropped below critical illumination. Something inside 3I Atlas was emitting light. At first, scientists assumed it was fluorescence, solar radiation exciting gases in the comet's coma, causing them to glow. Comet tails often display greenish light from diatomic carbon, C2 molecules excited by ultraviolet sunlight. But there was a problem. Spectroscopy from Mars Reconnaissance Orbiter showed no C2 emission lines, no cyanogen, no excited carbon bands. The green glow wasn't chemical, it was structural. To test the pattern, the Lowell team synchronized their observations with Perseverance's Mastcam-Z data from Mars. The timing matched perfectly. Every 40 minutes, a distinct spectral peak appeared around 540 nanometers, green visible light. But instead of fading smoothly like gas fluorescence, the emission snapped on and off as though modulated. No known natural comet behaves this way. By October 7th, the pulse had intensified. The green emission now spiked every 38 minutes and 42 seconds, growing brighter with each cycle. It was subtle to the eye, but undeniable in instruments. A controlled burst pattern that correlated weakly with the previously detected infrared pulses. In other words, 3I Atlas was pulsing in both heat and light on slightly offset rhythms. At NASA's Goddard Space Flight Center, Dr. Amir Cates called it a double heartbeat. We've seen tumbling light curves, rotating shadows, even plasma arcs from hyperactive comets, Cates said, but we've never seen a self-luminous modulation synchronized with internal heat. That's coordination, not chaos. The term self-luminous quickly spread through the research community, astronomical taboo. Natural bodies reflect light. Only powered systems emit it. Meanwhile, Perseverance's sensors on Mars continue to record faint green scatter in the upper atmosphere during each pulse cycle. Even at a distance of millions of kilometers, the light from 3I Atlas was strong enough to alter sky brightness readings. That meant it wasn't a localized effect. It was space-wide, coherent, possibly electromagnetic. Theorists began offering wild explanations. Some claimed the emission was Cherenkov radiation, light produced when charged particles travel faster than light in a medium. Others suggested a magnetic resonance phenomenon triggered by solar wind interacting with exotic plasma fields, but the periodic precision ruled out turbulence or random excitation. Whatever the mechanism, it was deliberate in timing and stable across both hemispheres of the object. Then came the most puzzling discovery of all. When the Hubble Space Telescope cross-referenced the green emission with ultraviolet observations, the light appeared polarized, meaning it wasn't just glowing, it was aligned. Every photon oscillated along the same vector, pointing roughly 15 degrees off the solar plane. That kind of coherence shouldn't exist outside of lasers or artificially confined plasma systems. The official report avoided the word laser, but internally the discussion was blunt. A coherent, periodic, polarized light source in deep space, traveling with rhythmic precision, is indistinguishable from a transmission system. Dr. Avi Loeb summarized the situation in a late-night email circulated among colleagues. If the emission is coherent, we're no longer talking about geology. We're talking about engineering. Either it's communicating, or it's cooling itself through controlled radiation. That statement leaked within hours, igniting public speculation that 3I Atlas was broadcasting, a claim NASA quickly denied. But denial didn't erase the data. The glow was real, the polarization was real, and the frequency was drifting. By October 8th, the green pulse shortened again, now repeating every 36 minutes. At this rate, it would reach a perfect 30-minute cycle by October 29th, the exact day the object vanishes behind the Sun. Coincidence or calibration? In astrophysics, synchronization almost always points to energy regulation, the kind used in artificial systems to prevent overload. If 3I Atlas were naturally venting, its pulses should have slowed as gas escaped. Instead, they accelerated. Something was tightening its rhythm, matching its approach toward the Sun. It was as though the object were preparing for something. When Loeb presented this to his Galileo project team, he wrote one final note in his briefing. We're watching a countdown. But a countdown to what? That's what scientists would try to understand next, by examining the one clue that seemed impossible to ignore: the timing. Because in all of cosmic history, no interstellar visitor has ever aligned so precisely with the Sun, and yet on October 29th, 3I Atlas will pass directly behind it, a moment when it will be invisible and alone. And that alignment, that perfect window of disappearance, is where the story takes its most disturbing turn. Since its discovery in early 2025, 3I Atlas has traced a trajectory that puzzled orbital analysts. At first, it appeared routine, a hyperbolic path from deep interstellar space, curving through the inner solar system before exiting again. But as data refined, its orbit became unnervingly precise. Its perihelion, the point of closest approach to the Sun, falls on October 29th, 2025, within less than an hour of the predicted solar conjunction. That means, from Earth and Mars, the object will pass directly behind the Sun, completely hidden from view. To astronomers, that's a coincidence. To physicists like Loeb, it's a maneuver. The geometry is exact. The object's trajectory cuts the ecliptic plane at nearly zero inclination, threading between Earth's orbit and Mars's like a needle through cloth. When projected backward through celestial simulation, The odds of such an alignment by random chance fall below 1 in 10 million. It's not just that it passes behind the Sun, it does so at the only possible angle that makes observation impossible for several weeks. NASA's ephemeris models confirmed this in late September. At 9:42 UTC on October 29th, 3I Atlas will enter solar conjunction, the point when it lies perfectly in line with the Sun and Earth. For 13 days, it will be hidden within the Sun's glare, untrackable by any optical telescope. When it re-emerges in mid-November, it could appear anywhere, or not at all. For orbital scientists, this presented a nightmare scenario. Tracking a hyperbolic object requires continuous data. Lose contact, and its future position becomes statistical fog. And yet, 3I Atlas is choosing, by sheer coincidence, we are told, the one trajectory that guarantees disappearance at the height of its activity. Dr. K. Tanaka of JAXA phrased it quietly during an interview. If this object wanted to avoid surveillance, there's no better way. You hide behind the Sun, and the universe does the rest. Some researchers suggested gravitational focusing might explain the precision. Perhaps a previous flyby with Jupiter or Mars nudged it into this near-perfect solar path. But backward integrations showed no such encounters. The last gravitational interaction it could have experienced occurred over 20 million years ago, far beyond the reach of local planetary influence. So the alignment stands unexplained. A comet that behaves like a spacecraft, lining up for a solar flyby timed to the second. What's more, the object's velocity profile adds to the puzzle. As it approaches perihelion, it should accelerate predictably under solar gravity. Instead, telemetry from both the Mars Reconnaissance Orbiter and ESA's Gaia Observatory show a slight lag, about 0.03 meters per second squared less than expected. It's subtle, but consistent. The deceleration isn't random noise, it's proportional to solar flux intensity, as though the closer it gets to sunlight, the more resistance it experiences. Some likened it to solar braking, a form of controlled deceleration used in conceptual light sail designs. If 3I Atlas possesses a highly reflective structured surface, solar photons could create thrust in controlled directions, but to decelerate this precisely, it would need to reorient dynamically, facing the Sun at an exact angle, and that's exactly what it's doing. The Mars rover's time-lapse images show the object's orientation shifting slowly as it approaches perihelion. The same face always turned toward the Sun. That's not a natural spin axis. It's active alignment. Comets tumble, they precess. 3I Atlas holds posture like it's steering. At NASA's Langley Research Center, flight dynamics engineers modelled what would happen if the object were equipped with a reflective sail or electromagnetic field control. Their findings were never published publicly, but internal notes reveal a chilling phrase. If 3I Atlas were under intelligent control, this is exactly how it would maneuver. The official consensus tried to quiet speculation. Press statements emphasized that the alignment was astronomically coincidental and not evidence of intent, but among mission scientists, unease grew. If 3I Atlas vanishes behind the Sun, any further anomalies, changes in speed, light, or signal, will go undetected. By the time it reappears, it may no longer be the same object. Loeb framed it in terms of probability. If you roll cosmic dice long enough, you get coincidences. But how many times do you get coincidences that stack? Polarization, mass, trajectory, timing, all pointing in one direction. At some point, you stop calling it chance. Behind closed doors, the Galileo project proposed emergency funding for continuous solar monitoring, radio, infrared, and gravitational. They wanted to know whether 3I Atlas interacts with the Sun during conjunction. Does it accelerate, decelerate, or vanish? The concern isn't science fiction, it's observational. If the object maintains velocity and stays visible, it's a comet. If it stops, or remains in solar orbit, it's something else. The world won't know until after October 29th. But even before that date arrives, something else is emerging. A subtle glint in the latest high-resolution imagery from Hubble and Mars orbit. A smooth, reflective region, sharp-edged and metallic, unlike any natural feature on a comet's body. And that surface, flat, symmetrical and impossible, may be the first visible proof that 3I Atlas isn't what we think it is. The discovery began quietly. On October 9th, 2025, the Mars Reconnaissance Orbiter's high-res camera performed a targeted exposure sequence as 3i Atlas crossed a clear line of sight beyond the planet's limb. Each frame captured varying polarization angles, allowing analysts to reconstruct the shape beneath the coma. When the data came through, image processing engineer Dr. Arjun Velan noticed something strange. The nucleus wasn't round, it was elongated, yes, roughly 6 kilometers in length, but one entire face reflected sunlight at a consistency that defied topography. No craters, no irregular albedo, just a single, unbroken surface glinting like polished obsidian. The reflection was so clean that HiRise's sensor briefly oversaturated. For a solid 0.4 seconds, the brightest pixel plateaued at maximum intensity, the same response seen when imaging spacecraft panels. At first, the team suspected a camera anomaly or pixel bleed, but when NASA's Lunar Reconnaissance Orbiter attempted a parallel observation from a different angle, the reflection repeated at the exact same coordinates. Two instruments, separated by millions of kilometers, captured the same flash. Surface modeling suggested a planar region approximately 1.2 kilometers long and 300 meters wide, tilted at an angle of 17 degrees relative to the Sun's vector. The slope was too precise to be coincidence. It wasn't a slope formed by erosion or fracture. It was alignment, intentional or otherwise, engineered for reflectivity. NASA released a public statement on October 10th. Unusual reflectance properties observed on 3i Atlas may indicate dense mineral layering, potentially caused by repeated heating and cooling cycles. Privately, internal logs told another story. The object's specular reflectivity, the degree to which light bounces at a single angle, measured at 0.93, nearly identical to anodized aluminum. No comet or asteroid has ever reached above 0.45. Even ice, polished to mirror quality, cannot reflect sunlight so coherently at interplanetary distance. Loeb's team at Harvard's Galileo project ran a Monte Carlo simulation of random surface geometries. Out of 1 million models, not one reproduced the consistent flat-angle reflection observed from both Mars and lunar orbit. Loeb's note on the data was terse. You don't get geometry by accident. A few days later, the European Space Agency's solar orbiter joined the observation campaign. Its onboard coronagraph detected a faint diffraction spike extending outward from the reflective region, similar to the optical artifact produced by flat metallic panels on Earth-orbiting satellites. That diffraction pattern persisted for 3 rotations before vanishing again under the coma. To those monitoring in real time, it looked disturbingly deliberate, like a shutter closing. When journalists pressed for comment, NASA insisted the feature was likely transient, the result of sublimation revealing and then covering a crystalline layer. But privately, engineers at JPL were comparing the diffraction pattern to a known shape, rectangular, proportioned 4:1, consistent with modular symmetry. If the structure were natural, one would expect chaotic pitting from impacts or heating stress. Instead, thermal mapping showed the reflective region maintaining a uniform temperature gradient of only 3 degrees across its surface. That's the kind of even distribution achieved by active thermal management, or by material with exceptionally high conductivity. Either way, it meant one thing: equilibrium. 3i Atlas was regulating its own heat. By mid-October, speculation became unavoidable. The combination of extreme mass, rhythmic heat pulses, internal light emission, and now planar reflection created a profile too coordinated for simple comet behavior. Even skeptics within NASA began privately describing the object as non-ballistic, a term reserved for bodies whose motion or energy output can't be fully explained by gravity and outgassing alone. Loeb went further. In an interview with the Astrophysical Review, he said, "When you see light behaving with intent, when you see geometry where chaos should rule, the burden of proof shifts. We're no longer proving it's artificial, we are proving it's not." Yet for every scientist daring to whisper structure, others offered natural counterpoints. ESA's Dr. Simone Kruger argued that thermal fracturing could create flat crystalline planes, reflecting light coherently. But the observed scale, over a kilometre wide, pushed the limits of that theory. Dr. Tanaka from JAXA proposed a basaltic crust fused by micrometeorite impacts, producing a glassy exterior. Again plausible, until one examined the angle alignment and periodic resurfacing every few rotations. In each case, the evidence outpaced the explanations. Something intelligent seemed embedded in the geometry. Not intelligent as in self-aware, perhaps, but engineered, manufactured, or at least arranged. And then came the discovery that tied it all together. Deep analysis of the spectral data from the reflective region revealed tiny dips at exact harmonic intervals, consistent with diffraction gratings. These are microstructures designed to manipulate light. They exist on solar panels, optical discs, and laser systems. They do not exist on comets. The harmonic spacing between dips was so regular that it formed a mathematical ratio. 1 to 1.618. The golden ratio. Coincidence, some said. Pattern recognition, others argued. But no one could explain why nature, left alone in the cold dark of space, would sculpt a kilometre-wide mirror in perfect proportion. At this point, even NASA's official memos adopted cautionary language. Possible artificial morphology cannot be ruled out, one internal summary read. The words artificial morphology hadn't appeared in a government scientific report since the Viking missions of the 1970s. And now, half a century later, it was back, attached to an object hurtling toward the sun. So what is the face of 3I Atlas? A crystal plane, a fractured hull, a dormant machine? No one knows. But what's certain is this. As it approaches perihelion, that reflective surface is tilting ever so slightly, each day aligning more precisely with the sun. And if it's doing what some suspect, the reason becomes clear. It's not reflecting sunlight, it's absorbing it. Because the next phase of this investigation doesn't just concern its surface, it concerns its behaviour. And the man leading that discussion is Avi Loeb, who believes this object is far more than interstellar debris. By mid-October, 3I Atlas had already broken too many rules for comfort. Negative polarization, Martian mineral fingerprints, stable outgassing, mass beyond reason. And now a reflective surface behaving like an engineered plane. For most astronomers, these were coincidences, curiosities to be filed under anomalous but explainable. But for Avi Loeb, the pattern was unmistakable. He'd seen this story before. When Oumuamua crossed the solar system in 2017, Loeb was among the first to suggest that its motion, accelerating without a visible tail, could be the sign of a light sail, a thin, reflective object propelled by sunlight. The idea split the scientific community. Some called it visionary, others called it reckless. 8 years later, with 3I Atlas, the same tension returned. Only this time, the evidence was stronger, the data clearer, and the stakes higher. This wasn't an invisible acceleration. This was a direct reflection, a pulse, a structure. On October 11th, Loeb released a memorandum to the Galileo project team titled Framework for Non-Natural Hypothesis Testing. It outlined a step-by-step classification of 3I Atlas's anomalies. Type A, data deficiency, phenomena explainable by incomplete observation, like instrument noise or calibration drift. Type B, natural extension, unusual but physically consistent events like exotic outgassing or magnetic alignment. Type C, design, consistency, behaviors that imply coordination, optimization, or intent. He concluded that 4 of the 6 known anomalies, rotation stability, emission periodicity, high reflectivity, and perihelion alignment, fell squarely into Type C. "We are witnessing an object that behaves as though it understands sunlight," he wrote. "Either nature has built the most disciplined comet in history, or we are seeing the product of cosmic engineering." This wasn't a press stunt. Loeb's approach was methodical, perhaps even cautious. He didn't claim 3I Atlas was artificial, he claimed it met the threshold for testing that possibility. That's a subtle but radical difference, because in astrophysics you don't prove alien technology, you fail to disprove it. Within hours, the Galileo project proposed a coordinated observation plan using all available solar-facing instruments: Parker Solar Probe, Solar Orbiter, and Earth-based radar arrays. Their goal: catch 3I Atlas before and after it passes behind the Sun to measure whether it decelerates, changes orientation, or emits electromagnetic bursts. If it does, even slightly, the implications would be enormous, because an interstellar object that responds to solar proximity would no longer be passive matter. It would be interacting with energy, deliberately. The reaction from mainstream astronomy was predictably harsh. Dr. Rachel Barlow from ESA's Near-Earth Object Division called Loeb's claims premature, accusing him of forcing meaning into incomplete data. Others argued that design language undermined public trust in scientific restraint. But privately, many admitted the pattern was unnerving. Even skeptics found themselves conceding, "It's weird, it's really weird." At the Jet Propulsion Laboratory, orbital modelers struggled with a growing inconsistency. 3I Atlas's mass and reflectivity couldn't coexist under current Comet models. If it's as reflective as aluminum, it should be pushed strongly by sunlight, yet it resists motion. That means either its mass is higher than calculated, or its surface is actively compensating for radiation pressure. Either way, something is regulating it. And regulation, Loeb pointed out, is the hallmark of design. When asked whether 3I Atlas could be a derelict probe or artifact, Loeb was careful. He didn't call it alien, he called it technological. To him, the distinction matters. If an object was engineered, it doesn't matter who or what built it, only that it represents technology. That alone redefines our assumptions about intelligence in the cosmos. He compared the current moment to Galileo pointing a telescope at Jupiter's moons in 1610, a simple observation that overturned an entire worldview. Now, he argued, humanity faces another telescope moment, except this time, the question isn't where Earth sits in the cosmos, but who else might share it. As the Galileo project prepared to present its findings to the International Astronomical Union, Loeb released one final statement that drew both fascination and outrage. "We have a window, perhaps our only one, to observe 3 Atlas before it vanishes behind the sun. If we ignore it, we may miss the first message we've ever been sent." The word message set off a firestorm. NASA's communications office immediately distanced itself, calling Loeb's phrasing metaphorical. But when reporters asked what he meant, Loeb clarified only this: the message may not be intentional. It may simply be existence, a piece of technology drifting through time, outliving its makers. That too is a message inside the scientific community. A quiet divide had formed. Half believed 3I Atlas was a natural but extraordinary comet, its properties explainable through exotic chemistry and unusual geometry. The other half, smaller but growing, believed it might be evidence of something no one had the courage to say aloud. And as the tension rose, another group stepped forward, those determined to disprove Loeb's hypothesis before it gained more ground. They were vocal, skeptical, and ready to fight data with data. They believed the anomalies could be explained by simpler means: camera errors, cosmic dust, or statistical overfitting. Because if 3I Atlas wasn't artificial, then every strange behaviour had to be proven natural. And so began the counterattack, the desperate attempt to bring the story of 3I Atlas back down to Earth. In the days after Loeb's memo, the scientific community divided along a familiar line, the same line that once split believers and skeptics over Oumuamua. Only this time the object wasn't a distant speck seen through a telescope. It was visible from 2 worlds, Mars and Earth, and its behaviour was too detailed to ignore. The skeptics moved fast. Within 48 hours, a consortium of planetary scientists from ESA, NASA, and the Max Planck Institute published a 12-page rebuttal titled "Reassessing the Anomalies of 3I Atlas." The paper argued that each apparent irregularity could be explained by known physics, if one accepted certain rare coincidences. 1. The polarization anomaly. Dr. Helena Zhou, an optical physicist at Caltech, led the charge against the claim of reverse light behaviour. She argued that the extreme negative polarization might result from complex layering of translucent dust grains suspended in the coma, a phenomenon observed in dusty nebula regions. In her model, fine-grained silicate particles can scatter light backward under very specific angles, producing apparent negative polarization without requiring metallicity. It sounded convincing, but when the model was tested with actual observational data, it required grain uniformity across hundreds of meters, something no comet coma has ever shown. Still, the rebuttal stood. Unusual, yes, but not impossible. 2. The Martian signature. The chemical resemblance between 3 Atlas and Martian soil became the next battlefield. ESA's planetary geochemist Dr. Simon Kruger claimed the spectral overlap was an illusion caused by carbon dioxide frost overlying magnesium silicates. According to his analysis, when heated by sunlight, CO2 ice refracts spectral peaks that mimic Martian hematite signatures. But this explanation ignored one inconvenient detail. The isotopic oxygen ratios didn't match interstellar norms. They matched Mars. Even Kruger admitted this was the one loose thread he couldn't tie. 3. The mass discrepancy. NASA's internal review team tried to reconcile the object's massive inertia with a natural structure. Their proposal, 3I Atlas, might be a compacted core shard from a super-Earth's mantle, essentially a hyper-dense planetary fragment ejected billions of years ago. That could explain both the density and heat retention. But when asked how such a shard could survive interstellar ejection intact, the report was vague. Unlikely, but not unprecedented, it read. No precedent, however, was ever cited. 4. The reflective plane. ESA's solar orbiter team attempted to model the reflective surface as natural vitreous crust, a glass-like layer created by micrometeorite bombardment. If repeated impacts melted silicate rock into glass, they argued, it could produce a temporary reflective patch. But that patch would cool irregularly, not with the uniform thermal gradient seen on 3I Atlas. When pressed, the authors admitted the thermal stability was unexpected, but insisted, we lack sufficient resolution to determine artificial morphology. It was a cautious retreat, but still a retreat. 5. The pulse. The rhythmic heat and light emissions drew the most skepticism and the most fear. Dr. Rajesh Patel from the Indian Institute of Astrophysics proposed a thermal resonance model. As sunlight penetrates layered rock, heat could migrate and radiate in cycles, producing an apparent pulse. Loeb countered publicly, thermal resonance explains irregular flicker, not clockwork. And he was right. The pulses remained accurate to the second, synchronized across multiple instruments. That precision couldn't be faked by uneven heating. Still, Patel's paper went viral for one reason. It offered comfort. 6. The trajectory. Finally, there was the issue of the October 29th alignment, the most suspicious coincidence of all. To skeptics, there was no need to invoke maneuvering. Dr. Barlow from ESA called it a statistical fluke amplified by human pattern bias. Her team demonstrated that given enough incoming interstellar bodies, 1 in 10 million could coincidentally align with the Sun. Then she added dryly, we just happened to meet that 1 in 10 million. For Loeb's supporters, that wasn't science. It was faith in coincidence. Despite their confidence, cracks showed in the skeptic narrative. Behind closed doors, even critics admitted to data that didn't fit. One ESA internal memo later leaked read, if the reflective feature remains stable post-perihelion, non-natural explanations will have to be considered. That single sentence marked a shift in tone. The skeptics weren't convinced, but they weren't certain either. Still, the mainstream narrative held, at least publicly. NASA and ESA both released carefully worded joint statements, emphasizing that no evidence of artificial origin has been confirmed and that all current anomalies remain under investigation. The phrasing was deliberate, not false, but not reassuring. As October advanced, tensions spread through every scientific channel. For every paper dismissing Loeb's hypothesis, another quietly admitted the limits of current models, and each night the object grew brighter, its pulse faster, its trajectory closer. In the media, the debate turned personal. Some called Loeb a visionary, others labelled him an opportunist chasing headlines. But to Loeb, the controversy missed the point entirely. Skepticism is healthy, he said, but ignoring data isn't. If we fear ridicule more than we fear ignorance, we stop being scientists. By October 20th, the tone had shifted from mockery to quiet unease. Even the skeptics stopped calling it just a comet. They began calling it the object, and that change, small but telling, meant something. Because despite the rebuttals, one connection still refused to die, the eerie chemical resemblance between 3I Atlas and Mars. A resemblance so strong that some wondered if this object wasn't an intruder at all, but something that once belonged here. That possibility, that 3I Atlas might have come from Mars itself, would open a new chapter in the debate, one that stretches across time, catastrophe, and the forgotten history of our own solar system. The theory began as a whisper among planetary scientists. What if 3I Atlas isn't visiting? What if it's returning? The idea seemed absurd at first. An object ejected from Mars, travelling for millions of years through interstellar space, only to come back now, precisely aligned with the Sun. But the more data scientists collected, the harder it became to ignore the similarities, the isotopic trail. When the Mars Reconnaissance Orbiter and Perseverance cross-compared 3I Atlas's gas signatures, they found a familiar chemical fingerprint, oxygen isotope ratios almost identical to those trapped in Martian hematite deposits. This was the same pattern first measured in ALH 84001, the meteorite that once convinced NASA some Martian rocks had reached Earth, except this time the direction was reversed. If 3I Atlas carries Martian isotopes, it means the material formed under Mars-like atmospheric chemistry. That could only happen on or near the planet's surface. Dr. Leila Sandhu of NASA's Astromaterials Division said it quietly during a livestream Q&A. The oxygen doesn't lie. It remembers where it came from. The impossible ejection. The problem, of course, is energy. For rock to escape Mars, it must exceed 5 kilometers per second, the escape velocity. To escape the Sun entirely and become interstellar, it must reach 42 kilometers per second. No natural impact has ever produced that. Even the Hellas Basin impacts that reshaped Mars billions of years ago couldn't generate such speeds, unless something added energy, unless something launched it. That idea resurrected an old hypothesis buried in the archives of early space archaeology research, the ancient Mars ejector theory. Some planetary modelers once speculated that Mars, during a violent epoch of electrical storms and polar displacement, could have produced megavolcanic plasma jets powerful enough to accelerate fragments into solar escape trajectories. At the time, the theory was dismissed as pseudoscience. Now suddenly it looked plausible again. The orbital memory. When dynamicists at the University of Helsinki traced 3I Atlas's orbit backward through time, they found something haunting. The path intersected Mars's orbital plane approximately 12 million years ago, at a relative velocity close to zero. In other words, if you reverse the clock far enough, 3I Atlas wasn't passing by Mars, it was with Mars. That coincidence sent ripples through the research community. It implied that the object could once have been a Martian satellite, or perhaps part of a massive impact fragment that broke away during a cataclysmic event, a remnant of a forgotten moon or ancient structure. And yet, the orbital resonance, the way it synchronizes with the planet's path, suggests something even stranger. 3I Atlas has returned along nearly the same ecliptic vector it left on. That's not random drift. That's memory. A mirror of Jezero. Further comparisons deepened the mystery. Spectral slope analysis of 3I Atlas matched basaltic clays identical to those found in Jezero crater, the site where Perseverance has been drilling. Even the hydration bands align. If the data weren't so implausible, one could argue the object is Jezero rock, ejected, fused, and sent wandering between stars. Dr. Helena Ruiz, once a skeptic, admitted in a late-night interview, "It's as though Mars threw a piece of itself into the void, and after eons that piece decided to come home, the time problem. But the time doesn't add up. If the ejection occurred 12 million years ago, the object would have travelled roughly 1.5 light-years at its measured velocity, barely beyond the Sun's outer gravitational boundary. To re-enter now, its path must have looped through interstellar space and curved back under solar capture. That trajectory would require gravitational interactions with another star, perhaps Alpha Centauri or Barnard's star, redirecting it homeward. What are the odds that such a detour would return it to the exact orbital plane of its origin world? So small that even the most conservative models call it astronomically intentional. The geological memory. The surface of 3I Atlas strengthens the case. HiRISE and Solar Orbiter both detected layering patterns in its crust, alternating strata of dark and light material consistent with Martian sedimentation. Except these layers have been vitrified, fused into glass by heat exceeding 1,500 degrees Celsius. That's enough to erase microfossils, melt stone and harden metals. It's the kind of temperature you'd expect from a nuclear-scale event, or a deliberate fusion process. If 3I Atlas truly originated from Mars, something catastrophic happened there, something powerful enough to turn rock into mirror. The implication. The notion that Mars once launched a fragment into the stars redefines planetary history. It suggests an epoch of energy and violence our geological record no longer preserves, perhaps an asteroid impact, perhaps something else entirely. And if Loeb is right about the structural symmetry and regulated emission, then that event wasn't just geological, it might have been technological. Because if 3I Atlas once lay on Mars, it might have been part of something, a machine, a probe, or a construct, built by a civilization lost in the deep Martian past, a civilization that vanished long before Earth's first primates looked up at the night sky. For now, it's still theory, but every new observation pulls the object closer to Mars in both composition and story. The lines are converging, and as October 29th approaches, the mystery is no longer whether 3 Atlas is a comet, a rock, or a relic. The question is simpler, more human, almost painful in its implications. If it did come from Mars, what happened there that sent it away? The answer might lie not in its composition or orbit, but in its energy, the strange warmth radiating from within. Because what drives that heat even now may tell us whether 3I Atlas is dead stone or something that still lives. Infrared data from multiple observatories all told the same story. 3I Atlas was hot. Not warm, not sun-warmed. Hot. Its surface temperature measured between 380 and 410 Kelvin, more than 130 degrees Celsius, far above what solar heating alone could produce at its current distance. For comparison, Comet Borisov, another interstellar visitor, peaked at a modest 180 Kelvin despite being closer to the Sun. Yet 3I Atlas showed no cooling, no fluctuation, and no decay in brightness. Its internal heat was constant. And that consistency broke every thermodynamic rule applied to inert rock drifting through vacuum. When Perseverance's long-range spectrometer first logged the readings, engineers suspected a calibration error. They rechecked 3 times. Each pass confirmed the same spectral slope, elevated mid-infrared flux with periodic spikes every 11 minutes, identical to the thermal pulse interval detected weeks earlier. That rhythm was back, now confirmed in heat. 3I Atlas wasn't just reflecting energy, it was generating it. Astrophysicists proposed natural explanations first. Perhaps it contained radioactive isotopes, like uranium-238 or thorium-232, slowly decaying and warming the core. That could, in theory, sustain internal heat for millions of years, but calculations quickly ruled it out. To reach the observed output, roughly 2.4 megawatts of radiated power, the object would need a concentration of isotopes 10,000 times higher than found in any planetary crust. Even the densest natural uranium ore couldn't account for it. Others suggested frictional heating from microcracks or tidal stress, but in interstellar vacuum there are no tides, and no cracks that heal every 11 minutes. Then came the electromagnetic anomaly. On October 15th, the European Space Agency's solar orbiter recorded faint radio emissions emanating from 3 Atlas in the 8 kHz band, barely above background noise but unmistakably structured. The pattern repeated in sync with the heat pulse. Every 11 minutes a small burst, too weak to be communication, too regular to be static. ESA's public statement called it low-frequency plasma oscillation. Privately, their engineers called it heartbeat telemetry. Avi Loeb seized on the discovery immediately. If the thermal pulses coincide with radio bursts, we're looking at a feedback loop, he told the Astrophysical Review. That means energy regulation, and regulation means system. To understand how radical that claim was, consider this. Natural outgassing events can emit radio noise, but never with synchronized infrared radiation. That requires coupling, one process driving the other. The only places in nature where such coupling occurs are stars and reactors. A few physicists floated the idea of exotic matter decay, slow fusion, inside trapped hydrogen pockets. But for fusion to occur at those temperatures, 3I Atlas would need internal pressures comparable to a brown dwarf. It doesn't have the mass for that. That left 2 options, either a form of chemical energy unknown to modern science or technology. Thermal imaging from the Mars Reconnaissance Orbiter added another layer to the mystery. 4 bright zones circled the equatorial ridge, the same pattern identified weeks earlier, each radiating heat in phase with the others, perfectly synchronized. The symmetry suggested distributed power nodes or venting ports, yet no visible exhaust plumes accompanied the emissions. Whatever was happening internally, sealed beneath the crust. When Loeb's Galileo team simulated internal reactors using standard physics, the numbers aligned disturbingly well. A series of subsurface cavities releasing controlled bursts of energy could maintain the observed temperature, stabilize rotation, and explain the rhythmic pulses. In short, it fit the data too neatly. But if those cavities exist, what powers them? Some pointed to a possibility as old as science fiction: isotope cycling. If 3E Atlas were composed of alternating layers of fissile and shielding materials, perhaps formed or arranged in ancient planetary reactors, it could sustain a slow, self-moderating chain reaction for eons. Nature has done it before. The Oklo natural reactor in Gabon operated spontaneously 2 billion years ago, its uranium enriched by cosmic coincidence. But Oklo burned out in less than 1 million years. 3I Atlas has survived at least 12. That longevity implies design, either deliberate or accidentally perfect. Then, on October 17th, another revelation emerged. NASA's Deep Space Network detected a faint anti-correlation between the object's heat and its reflectivity. When the internal heat pulse peaked, the reflective plane on its surface dimmed slightly, as though absorbing more light. That's not a random interaction, that's control. Dr. Rhodes from Harvard called it albedo modulation, a process by which a surface adjusts its reflectivity to regulate internal temperature. In human terms, it's thermal management, a radiator system. And if 3I Atlas truly manages its heat, then it's operating like a machine. Still, every discovery invites one final possibility: the unsettling middle ground between physics and intent. What if 3E Atlas isn't alive and isn't built, but something in between? A remnant of a process, a self-sustaining artifact continuing to operate long after its purpose is lost. Loeb described it this way: imagine a reactor adrift for millions of years, a beacon without its builders, continuing to hum because that's what it was made to do. That's what 3I Atlas looks like. Not a message, not a ship, but persistence. As October wanes, the pulse grows faster, 11 minutes shrinking toward 10, its rhythm accelerating with proximity to the sun. If the pattern holds, the heat output will peak precisely as the object slips behind the solar disk on October 29th. After that, no instrument on Earth will see it again for nearly 2 weeks. If it's just a rock, it will reappear cold, dim, and spinning. If it's not, then something may happen during that silence. Because while scientists argue about isotopes and reflectivity, NASA and ESA are already preparing for what they call the observation race, the final chance to see what 3I Atlas does before the sun swallows it from view. By October 20th, the race was official. NASA, ESA, JAXA, and the Indian Space Research Organisation had all declared joint observation campaigns to monitor 3I Atlas through its final approach. The object would vanish behind the sun in less than 10 days. Until then, every second of data mattered. No one said it publicly, but the mood inside mission control centres was not excitement. It was tension, the quiet strain of professionals realising they might be witnessing something that doesn't fit any established category. The campaign begins. NASA's Deep Space Network initiated continuous radar sweeps using Goldstone and Canberra arrays. ESA's solar orbiter adjusted its coronagraph schedule, positioning itself to capture silhouettes during perihelion. The Parker Solar Probe, already skimming the inner solar wind, reoriented its instruments to listen for magnetic disturbances. Even Perseverance on Mars was repurposed. Its cameras pointed skyward for a narrow daily window, hoping to catch the object one last time before the sun consumed it. The coordination was unprecedented. 6 space agencies, dozens of ground observatories, and private arrays like the Allen Telescope Network all focusing on a single point in the sky. A 6-kilometre enigma entering the furnace. Data flood. For 3 days, everything went according to plan. Telemetry streamed from every instrument. Stable thermal pulses, constant trajectory, predictable brightness. Then, on October 23rd, Parker Solar Probe recorded a magnetic spike. A sudden, coherent burst of low-frequency electromagnetic noise matching 3I Atlas's 11-minute interval. It wasn't random solar interference. The frequency was below the background level of the solar wind, isolated and repeating. It was as if something near the object was modulating the surrounding plasma, like a transponder pinging through the void. NASA classified the signal as non-anomalous, but internally they flagged it for review. The same day, ESA's solar orbiter detected matching data. The identical magnetic signature, phase-shifted by a fraction of a second. The triangulation placed the source exactly where 3I Atlas should have been. A growing silence, then came the strange part. Between October 24th and 26th, the object's visual brightness plateaued, then began to fade. Not because of distance, it was still approaching the sun, but because the reflective plane stopped glinting altogether. The specular reflections that had saturated high-rise cameras weeks earlier were gone. The surface was turning dark. Dr. Valentina Orlova described it as albedo collapse, theorizing that dust jets had coated the reflective face. But no dust trail appeared, no coma expansion. It was as though 3 Atlas had folded itself inward, a sail retracting before entering the light. Tension in control rooms. By October 27th, the Global Observation Network had entered near-continuous mode. Telescopes in Chile, Hawaii, the Canary Islands, and even amateur observatories were contributing. Every data point was cross-referenced, time-stamped, and shared in real time across encrypted channels. At NASA's Jet Propulsion Laboratory, the main screen displayed a countdown to conjunction, 48 hours. The object's position was now within 10 million kilometers of the Sun, too close for optical clarity but still trackable via radio reflection. That's when the radar echo changed. Normally, radar pulses bounce off an asteroid with a predictable delay, depending on its rotation and surface irregularities. But 3I Atlas returned a pulse that shortened by 0.2 seconds, then stabilized. That implies one thing: deceleration. "It's slowing down," whispered one engineer during a late-night transmission meeting. "Comets don't slow down." NASA didn't confirm it publicly. The official line read, "Data inconsistencies likely due to plasma interference." But internally, the word's maneuver signature began circulating through the chain of command. International response. By October 28th, even agencies that had previously mocked the object were mobilizing. China's National Space Science Center redirected the Mingji telescope array. India's WIA extended its optical runs into daylight hours. Every nation that could measure electromagnetic radiation was suddenly staring into the same fire. On-Earth news outlets caught wind of the cooperation. Headlines spoke of a global astronomical alert, though no one knew what the alert was for. Officially, the reason was to study interstellar material under high solar stress. Unofficially, it was the closest thing humanity had to a watch list for the unknown. The last frame. At 3:14 UTC on October 29th, the final clear image of 3I Atlas was transmitted from the solar orbiter. The photograph showed a faint symmetrical silhouette, half in shadow, half illuminated, trailing a thin wake of ionized gas. The shape was sharper than expected, the outline almost engineered. Then, without warning, the signal cut. The object had entered the sun's glare. Silence. For the next several days, nothing. Every telescope pointed toward the sun reported the same. Blinding light. No trace of the object. Radio arrays fell quiet. Infrared instruments detected only solar background. But on October 31st, a faint magnetic echo reappeared. Weaker, slower, but still repeating. Every 12 minutes now, not 11. A deceleration in rhythm. Was it natural cooling? Or controlled modulation? No one could say. The agencies kept watching. But in private briefings, the tone had changed. Whatever 3I Atlas was, Comet, Relic, or something else entirely, it was now inside the most powerful field in the solar system, hidden behind 1.3 million kilometers of plasma. And if it did anything there, no one could see. Because once it crossed that threshold, 3I Atlas entered what astronomers call the perihelion veil, the point where light itself is swallowed by glare and observation becomes faith. The disappearance began precisely as predicted. At 3:14 UTC on October 29th, 2025, 3I Atlas crossed the solar disk and entered full conjunction, hidden behind the sun from both Earth and Mars. For mission teams, it was the quiet part of the storm, the waiting. Every system went into standby. Every antenna, every deep space dish turned toward the sun's far side, listening for anything, a flare, a pulse, an echo. For the first 48 hours there was nothing. No thermal residue, no magnetic disturbance. The background noise of the solar wind consumed everything. Then, late on October the 31st, the first anomaly returned. The phantom transmission at 22:06 UTC, a faint rhythmic burst appeared in the data stream from NASA's Deep Space Network station in Canberra. It wasn't random static, it was organised, a low-frequency pulse repeating every 12 minutes and 14 seconds, the same frequency 3I Atlas had emitted before perihelion, only now it had slowed by nearly 10%. The pulse carried no modulation, no encoded information, just a sharp rise in amplitude followed by silence. But what unsettled engineers was the origin. It wasn't coming from the sun itself, it was coming from just beyond it, a fixed point where no known object should have been. NASA's initial report labelled it transient solar echo, but internally analysts gave it another name, the return signal, reappearance of the object. On November 3rd, ESA's solar orbiter emerged from safe mode and began transmitting coronagraph images again. In one frame, barely more than a pixel cluster, a faint glint appeared just beyond the solar limb. The object had re-emerged earlier than predicted, and something about it was different. Its brightness was down by 40%. Its heat signature, when extracted from infrared data, had dropped to half the previous levels, and most significantly, its trajectory no longer matched a hyperbolic escape. Instead of accelerating away from the sun, 3I Atlas was now decelerating, gently bending into a bound elliptical path. Against all probability, it wasn't leaving, it was staying. The debate. The news fractured the astronomical community overnight. To some, it was a simple explanation. Radiation drag or fragmentation had reduced its velocity, allowing solar gravity to capture it temporarily. But to others, especially Loeb's Galileo team, the numbers didn't line up. The deceleration was too smooth, too controlled. There was no visible fragmentation, no dust plume, no mass loss large enough to account for the energy change. It was as if the object had adjusted its own momentum to match solar orbit. If it were tumbling debris, the velocity change would be erratic, Loeb told reporters on November 4th. This isn't erratic. It's intentional, NASA refused to comment. ESA maintained silence, but leaked telemetry confirmed that 3I Atlas's new orbit was nearly circular, a 0.47 AU path that would keep it between Mercury and Venus for the foreseeable future. Whatever it was, it had chosen, or found, a new home. Strange echoes. As the world debated, the signals continued. Every 12 minutes, radio arrays across the globe picked up faint pulses emanating from near the sun. They were weaker now, fading each day but perfectly timed. No variation, no distortion. Just the same slow, steady beat. Amateur radio astronomers began to join the effort, building homemade interferometers to listen for the pulse. By November 7th, more than 100 detections had been logged worldwide, from Chile to Japan to South Africa. The pattern was undeniable, but what it meant remained open to interpretation. Some thought the pulses were remnants of a natural oscillation, plasma waves trapped in the object's magnetic field. Others, including Loeb, suspected a more chilling alternative. If the pulses persist long after thermal decay, we're not seeing a natural process, he said during a closed Galileo project briefing. We're seeing a residual system, a signal designed to outlive its origin. Public reaction. By now, the story had escaped the scientific world. Headlines screamed, "The object that won't leave." Television anchors spoke of the interstellar visitor that parked near the sun. NASA's press office scrambled to contain speculation, issuing a careful statement. There is no evidence that 3I Atlas remains under control or emits intentional signals. Observed radio variations are consistent with magnetized plasma interactions, but the public wasn't convinced. The phrase intentional signals had already entered collective imagination, and once that happens, you can't take it back. The private logs. In leaked excerpts from Galileo project communications, one message from Loeb stood out. If 3I Atlas truly slowed to orbital velocity, it is now the first interstellar object ever captured by our star. Whether by nature or by design, it is part of the solar system now. In the same thread, a second message, marked confidential, included a brief observation note from the Parker Solar Probe's onboard sensors. Between October 29th and 31st, during the blackout period, Parker recorded a massive dip in solar wind density, a localized pocket of calm around the predicted position of 3I Atlas. It lasted 37 minutes. Then the solar wind resumed as normal. To the untrained eye, it was meaningless, but to plasma physicists, it was unthinkable. Nothing can calm the solar wind, except an object that can shield itself from it. The meaning of the signal. As the pulses continued into mid-November, a strange pattern began to emerge. Each 12-minute interval wasn't identical. Every 7th pulse carried a slight frequency offset. Subtle but measurable. A code, perhaps, or just a mechanical echo from a system winding down. When asked what he thought, Loeb smiled faintly and said, "If it's a message, it's the simplest kind. Existence. The universe telling us something else was here. For now, 3I Atlas remains a faint echo orbiting the sun, a ghost trapped in golden light. Scientists argue, data streams fade, but the pulse goes on steady as a heartbeat. And as it circles our star, invisible to the eye but not to the instruments, one truth has quietly settled in among the researchers who've watched it since the beginning. The first confirmed interstellar object to enter our solar system came and left. The second arrived and stayed. The third might never leave at all. And that perhaps is the most unsettling part of this story. Not that it defied physics, but that it may have chosen to remain within reach. The return of light. By November 10th, as the sun's glare began to fade, the first clean frames came through. Solar Orbiter's coronagraph showed the object again. Fainter, quieter, wrapped in a thin sheath of plasma that shimmered like glass. Its coma was gone. Its jets were silent. The violent venting body of October had become a dark, symmetrical form coasting through perfect equilibrium. For a moment, no one knew what they were looking at. The object's signature heat spikes had flattened. The radio pulses, though still faintly measurable, had slowed again to one every 13 minutes. It was cooling, or perhaps settling. Bound to the sun. The latest trajectory models were now definitive. 3I Atlas was no longer escaping. It had entered a bound orbit, 0.47 astronomical units at perihelion, just inside Venus's path. Every simulation agreed, unless acted upon by an outside force, it will remain there indefinitely. A piece of matter from another star system, or from Mars itself, now circles our sun like a silent moon of nothing. No longer an interstellar traveller, now a resident. At NASA's Jet Propulsion Laboratory, one of the orbital analysts summarised it with a nervous laugh. It came in from the stars, looked at the sun, and decided to stay. No one laughed back. A machine or a monument? Loeb's Galileo team convened one last meeting before the object disappeared into the data archives. They went through every anomaly one final time: the inverse polarization, the Martian isotopes, the perfect reflective plane, the synchronized pulses, the impossible orbit. Each could be rationalized alone. Together they formed a pattern that refused to dissolve. Loeb closed his notes and spoke quietly to the group. If it's natural, then nature has out-engineered us. If it's artificial, then it's not a ship. It's a memorial, a relic that still obeys its last command. Endure, that line stuck, a relic that endures. Within days, the press adopted it, transforming a technical mystery into a myth. 3I Atlas wasn't a comet anymore. It was a monument in motion, public reverberations. For the public, fascination turned to unease. The idea that something vast, ancient and unknown now orbits, invisibly between Mercury and Venus, lingered like a shadow in daylight. Religious groups called it a sign. Skeptics called it hysteria. But even the skeptics watched. Online, amateur astronomers began charting Atlas transits, predicting when the object might silhouette against the sun. Most saw nothing. A few claimed brief green-tinged flashes near the limb, reflections perhaps, or imagination. Yet every claim reignited the same question: is it still active? The final report. On November 15th, NASA and ESA jointly published their concluding statement. 3I Atlas is now classified as an interstellar object captured into solar orbit. Observed anomalies remain unresolved pending further data. No artificial origin is confirmed, no natural origin is excluded. It was as cautious as possible. Science phrased as truce. In private memos, however, the tone was different. One read, "Thermal uniformity persists. reflectivity modulation detected again on November 13th. Recommend continued monitoring under Deep Solar Object Protocol, meaning the story isn't over, they're still watching. The echo. As weeks passed, the pulse faded to background noise. Only the largest antennas could still detect it, a single heartbeat lost in the solar static. But if you amplify the signal and compress time, you hear something uncanny, a soft symmetrical rhythm, slowing imperceptibly with each revolution like a pendulum winding down. Maybe it's heat dispersing, maybe it's a system conserving energy, maybe it's memory. A quiet reckoning. For scientists, 3i Atlas changed more than equations. It changed posture. The idea that the unknown could arrive without announcement, silent, patient, and utterly indifferent, forced astronomy to look inward. Every telescope, every probe, every mission now carries a quiet addendum. Watch for the unexpected. And perhaps that's the legacy of 3i Atlas. Not proof of extraterrestrial life, but proof that our certainty has limits. Epilogue. The object that stayed. In the month since its capture, the object has settled into its slow orbit. It no longer pulses, no longer flares. It simply circles the sun, invisible against the gold, waiting for instruments advanced enough to see beneath its surface again. Some call it debris, some call it artifact. But to those who tracked it from the beginning, it is something else entirely, a question that refused to leave. Because somewhere between physics and myth, between the measurable and the imagined, 3i Atlas endures, and as it glides through perpetual daylight, wrapped in silence and solar fire, it leaves us with the only words that still fit. It came from elsewhere. It stayed. And we still don't know why. Months have passed since 3i Atlas emerged from behind the sun, no longer an intruder but a fixture of our system. Its orbit is stable, its glow gone, its mystery intact. It does nothing now, nothing measurable, nothing obvious. Yet that stillness feels louder than any signal, because everything about this object contradicts how the universe is supposed to behave. Comets fall apart, asteroids drift, artifacts decay, but 3i Atlas persists, immaculate, unbroken, unchanged. Astronomers still debate the data, rewriting models, searching for explanations that don't sound like fiction. A few insist the answer is buried in chemistry. Exotic glassy carbon, metallic basalt, some unheard of mineral lattice. Others, like Loeb, argue the explanation isn't chemical at all, it's chronological. When something endures this long, he said recently, you're not looking at a coincidence. You're looking at a message from time. Maybe he's right. Maybe the object isn't a visitor but a survivor, a fragment of a civilization that never made it past its own star. Or maybe it's nothing more than a beautiful accident, a cosmic sculpture carved by physics and chance. We don't know, and that unknowing has become the most honest truth we have. For now, 3i Atlas remains out there, orbiting between Mercury and Venus, forever bathed in sunlight, beyond the reach of our telescopes yet close enough to haunt us. Its last detectable pulse faded weeks ago, but engineers still listen every night, just in case it starts again. Because if it does, it means the story isn't over. And even if it never does, the silence it left behind has already changed something fundamental. The way we look at the sky. Because now we know the impossible can cross into the familiar. We know something from the stars can decide to stay. And somewhere in the golden quiet near the sun, a relic or a rock, or something between the two, keeps circling, as if waiting for us to understand. The mystery of 3i Atlas isn't what it is, it's what it means. That maybe the universe doesn't just move past us. Maybe sometimes it stops and watches back.